Alright, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is the final sections, sections 16.9, 10, and 16.11 in AP Chemistry. So, before we get going into these notes, there's a couple of objectives I would like you to meet by the end of this lesson. So, objective number 1. Predict whether a particular salt solution will be acidic, basic, or neutral. Objective number 2, explain how acid strength relates to the polarity and strength of the HX bond. And then objective number 3, define an acid or base in terms of the Lewis concept. So, what we have in front of us, and I'll warn you that this is a little bit more definition heavy, so we'll be pausing the video and writing the definitions down and then going through just actually verbally explaining some things here. But we get to this process of hydrolysis, and we actually started to talk about this concept in section 7 without giving it this definition, without giving a specific name, and here is this specific name. So hydrolysis is just defined as the process in which salt ions can react with water to form either OH- or our hydronium, or H+ ions. So let me pause and write that down. Alright, so there is that written definition. Now, I don't want to write this stuff down. This is the part I was talking about just verbally going over. So, as salt, we saw that process with sodium hypochlorite where we were able to actually calculate the pH of that salt solution that was dissolved in water, and that's because that hypochlorite ion reacted with water and formed ions. And from there, we were able to calculate our, or the equation gave us our POH, and we were able to calculate that OH- ions. Now, again, verbally just going over this, there are 3 things that could happen. Well, I guess 4. 1, we look at strong acids, and if we dissolve a salt, the anion, the negative ion, what happens there is that this anion is going to have a negligible or little tendency to abstract protons from water, and most importantly here, does not affect the pH of the solution. So in a strong acid, an anion is going to have no effect on the pH. Basically, not enough of that H2O is being utilized by that anion to have a huge difference in our pH. Now, a weak acid, on the other hand, if we have a dissolved anion, so a negatively charged ion, an anion is going to have an effect to abstract protons from water, and most importantly here with a weak acid, an anion will affect the pH of the solution. Now, our other side of the story here is what we have with our cation, our positive ion that forms when we have a salt in solution. So a cation, if we have a polyatomic or a metal ion, just a single, let's say Na+1 ion, both of those things, a cation, when it reacts with water, is going to cause a decrease in pH. And it's going to cause a decrease in pH is because some of that ionizable proton, basically what's going to happen there is there's going to be a formation of more of those H+ ions. So again, verbally went over that. I don't think there's any need to write that down. But now what we can do here is we can move down to these guidelines that really drive us and dictate what exactly happens when we have certain salts. So, number 1, you can read along here, are salts that are derived from a strong acid and a strong base are neutral. So an example of this is NaCl. So our example from NaCl is this. When it is broken down, and it's probably best to show this, it breaks down into Na plus Cl minus. Now, these things right here, what we're trying to talk about here is sodium chloride itself. That salt is neutral. Now, this right here is going to be an anion. And because it's the conjugate base to HCl, hydrochloric acid, it is going to have virtually no effect on the pH, or a pH change so small, we're not even able to calculate the difference. Now, if we move down here to our second point here, it says salts derived from a strong base and a weak acid are basic. So let's go back to our example we've done a problem on in section 7. We looked at sodium hypochlorite. And so, made a mistake there. Should be NaClO. And if we break this down, again, what happens here is this. We have our, did it again, ClO minus ion that is formed, and both of these things should be aqueous. And what happens here? This right here, ClO minus, it is the conjugate base to our hypochlorous acid. And so that's why when we have ClO minus in solution, this becomes basic. So there's an example of this. Now, we get a little bit more complicated down here in 3 or 4, but it does give you some experience, or it does give you some real-world examples with how this business can affect our pH. And so we get down here to number 3. It says salts are derived, or that are derived from a weak base or a small cation with a 2+ charge or greater, and a strong acid are acidic. So one example that we have with this is, let's use aluminum chloride. So our example with aluminum chloride, we have AlCl3. Now when it is broken down in or as a salt, what happens is we get Al3 plus 3 Cl minuses. Now, again, I should be writing aqueous. Again, what happens here is this. Our salts that are derived from a weak base, or a strong acid, which is the case here with this Cl minus, are acidic. So what happens here is that these things will be an acid in that particular compound, or when we dissolve it in water. Now our fourth example here is this. It says salts derived from a weak acid and a weak base can either be acidic or basic. So one great example here that we have is ammonium chloride. So NH4, or excuse me, ammonium cyanide, how about? So ammonium cyanide, when it breaks down into our solution, and this is probably our best example, or at least the best example I can explain, we have a couple of things going on, and I'm going to take some time here. Number one, NH4 plus, this guy right here, this substance, is a weak acid. And Cn minus, this is the conjugate base, or a weak base. And if we dissolve this in solution, we form our HCN, and we form from water, get that OH minus. So in each of these examples, we can apply which one is going to be acidic and which one is going to be basic. So, again, I just wanted to give you a snapshot of what this is, give you a little bit more broad picture as to what happens when we dissolve a salt. The best examples that we're going to get are in chapter 17 when we go over, or when we talk about the common ion effect. We get into more detailed calculations about what that happens. But again, just giving you a snapshot about what is happening, and now we can move down into some factors that affect acid strength. And this is probably more important than the gibberish that I just went over. And so we start out with this, our HX substance. Now remember, our H is going to be what allows us to define an acid at this moment as an acid. So anyways, let me read this. An HX bond, which we have here, must be polar with a partial positive around our H plus and a partial negative around our attached substance X. So let me pause and write that down. We'll do a little bit more explaining. All right, so there is that written definition right there, and a couple of things that I should note as we go through this process. Number one, this thing that we've been labeling as X, this is what is attached to our H plus, and really we could call this the basic substance here. So I'm going to put in simple terms attached to our H plus. So it's whatever is attached to H plus. It could be a variety of things, but we have to be able to think about what affects our strength of our acid. We have to think about the bond polarity. We have to, number one, have to have some of this bond polarity business to be able to attract that H2O or involve that in our solution process. Number two, we have to have an ionic hydride, or if we have an ionic hydride, that's a better statement. If we have an ionic hydride, the HX bond must be polar with our H, which is now going to have a partial negative, and our X, which has a partial positive. And an example of this is sodium hydride. So let me write that down. All right, so there is that definition here. Ionic hydrides, you honestly don't see them very often, but we just flip the substance here. We flip what is partially negative, now the H, and what is partial positive, that item or those atoms attached to that H. Now, we get into bond strength. So this is probably one of the most important things here. The HX bond must be weak enough to be broken. So let me pause and write that down. All right, so there is that definition. Again, if we don't have an H plus break off and form in our solution, then we no longer are going to have the ability to have that acid, that Bronsted-Lowry definition of an acid. Now, another thing that affects our acid strength is going to be the stability of that conjugate base, which we have defined as that X to the minus. Now, here is our typical trend for this. The greater the stability of the conjugate base, the more acidic the molecule. So let me pause and write that down. Okay, so to sum this all up, the whole point of these four things, and really from the last page as well, is this. The molecular or atomic structure along with periodic trends affect the acid strength. So the point about this is we've done a bunch of calculations and we've gone through that whole process there, which is really important to see that. But we have to remember those values, the reason that we have those values, the reason that a certain substance has a pH or allows so many H pluses to break off and become those hydronium ions, it all comes back to what we talked about, or what really the basis of chemistry is, and that's that molecular and atomic structure of those atoms or molecules, or in the case of ionic substances, those formula units there. And then also periodic, and I'm going to draw an arrow here, I forgot a word, periodic trends. Make sure you include that, periodic trends. I know it's small, but we can tie all of that back in here to explain this. So we're going to get into just a few more things that also factor into that structure business about what happens with our acids in terms of determining their strength and really determining their behavior. So again, we'll go over some definitions. I don't expect you to be an expert in this, but with binary acids, and here's the periodic trends. In binary acids, the general periodic trends is associated with the strength of the acid. Okay, so let me pause and write that down. All right, and binary acids. I should be clear or clarify this. Binary acids, you have an H and then X, which in this case, our X is just one other element. Now, you could have multiple of those elements, but you only have H plus something else. Now, here is our general periodic trend that we have for binary acids. 1, acids are going to get stronger as they go down a group. So acids get stronger down a group, and then bases are just the opposites. Bases, substances that are bases, get weaker, or their strength decreases down a group. Now, our other two things, they're a little bit more organic related. They start to really focus in or hone in on that molecular structures. But we start out here with oxy acids. And so an oxy acid is just defined as an acid that contain an attached hydroxyl group, a dash OH, and often have additional oxygens bound to their central atom. And so the important thing about this is that the strength of the atom depends on what is attached to the OH or the hydroxyl group. So let me pause and write that down. All right, so there's our definition. I know it's kind of wordy here, but the bottom line up front with oxy acids here is they have an attached hydroxyl group. Remember, we looked at this a little bit when we talked about organic structure. There's more to it than this, but what I'm going to say is structure matters, and what and where that OH or hydroxyl group is attached does make a difference. Now, the last one we'll talk about here is carboxylic acids. And we talked about carboxylic acids a little bit when organic chemistry was introduced. And so organic or carboxylic acids are defined as acids that contain a carboxylic acid attachment or group. And these things include things like acetic acid, benzoic acid, formic acid. They're very common they're very common in organic acids. So I'll write this down, I'll explain it a little bit, and we'll move in probably the most important part of this portion of notes. All right, so there is that definition here. The bottom line here, really for the number 2 and 3, these things are getting into organic structure and how we really define an acid and how we can classify on its strength gets a little bit more complicated than what I want to get to in this class. Now, bottom line up front in those 3 last pages, I want you to have a baseline of what affects, more so than just the calculation, what affects the acid strength. You have some notes to reference, you have some things to look back, and some problems to do if you want to understand more of this. This is not going to be the emphasis. Now, the emphasis, though, probably the most important thing out of this is Lewis acids and bases. So we started out and we said an acid and a base. We started out with that Arrhenius definition. And in an Arrhenius definition, we were really limited about what was actually defined as a acid or base. Then we moved to a Bronsted-Lowry base and acid. And that said, hey, an acid is an H plus donor or a proton donor, and a base is a proton acceptor or H plus acceptor. And that really broadened what could be classified as a acid and base. Well, the problem, and maybe you've seen it, the problem with organic substances is that oftentimes that H is not lost, is not transformed, and so we have to have another way to define acids and bases. So a Lewis acid and base is going to allow us to make a definitions of acids and bases that focus on electrons, and this is important because it includes into acid and base, or into that category of acids and base, substances that do not involve a proton transfer. So let me pause and write that down, and then we'll get into the specifics down below here. All right, so here is everything written down that I explained, and this is the big thing, electron transfer. A lot of chemical reactions involve some type of electron transfer. Not all transfer a proton or transfer that H plus, but now we can have a more broad definition of what an acid or a base is. So let's get down to the nitty-gritty details here, and let's talk about what a Lewis acid is. So a Lewis acid is an electron pair acceptor. And a Lewis base is an electron pair donor. All right, so to explain or to go through what a Lewis acid and base is, I have an example reaction. This is an organic reaction here. And so what is going to happen here? I have the structures of both ammonia and boron trifluoride. Now, boron trifluoride, remember, is that exception to the octet. That's why it has this open area here. It's okay with just having 6 valence electrons. But what happens in this chemical reaction, and what I'm going to mark here in yellow, is where do those electrons go? And so when this happens, what we end up with is we still have, this should be our H's, that's an H. We still have N connected all to H's, and then we form this bond, and I'm going to bold, make this bold here, and we're going to get boron. We're going to get boron trifluoride, and that is a reaction where because, and this is the emphasis here, because NH3 donated a pair of electrons, donated both of these electrons to form this bond, this right here, NH3, is our Lewis base. And now, because BF3 accepted these electrons to be able to form this covalent bond, this right here, the BF3, is our Lewis acid. All right, so hope you have learned a lot. Again, the importance is giving you a broad overview to emphasize, hey, acids and bases, we can do a lot of calculations, but why they have those calculations, that's why we went through those first 3 pages. And then this definition of an acid and base with the definition of what Lewis defined it as gives a lot more things, or more and more substances can be classified as acids and bases. All right, so that concludes another episode of Science with Surback. As always, if you've liked this video, don't be afraid to click that thumbs up button, and never forget to subscribe.